Hello, welcome to our next experiment. This one is on calories in food. Now, when you go to a restaurant or when you buy a food product, it often gives you the number of calories. So the obvious question is, well, how do they know that? Well, today we're going to find out. We're going to take measurements of food and compare that to others. Here are a bunch of foods that we use during our experiment. The students get to choose which food they're going to burn. They can burn Triscuits or Cheerios or nuts. Nuts tend to work fairly well because they're full of oil and burn nicely, but the calories are calculated the same in any case. So first of all, what is a calorie? Calorie was an earlier measurement. It's not part of the ISO system, but it's easily related to joules, which is our normal measurement. And what's a joule? Well, here's Mr. Joule, James Joule, 1845. He came up with the concept of the relationship between mechanical energy and thermal energy. Before that, people understood that things were hot and cold, but they had no quantitative measure of the heat energy. They could measure the temperature, but they couldn't measure the energy. So Mr. Joule did a groundbreaking experiment, made him famous, and in fact he got his namesake after the energy unit called the joule. And here's his experiment. What he did is he took a mechanical weight with a little pulley, and he let the weight go down from high to low, transferring its energy to a little paddle wheel. And so what happened is the water inside of this tub got warmer. So he could now relate mechanical energy to thermal energy, which was a breakthrough. So, and he got named as the energy unit, the joule, for that work. So here's a little bit of text on his data. The point is he got a result that's pretty darn accurate considering the nature of the experiment and the equipment they had in those days. Again, this is over 100 years ago. So one question we have is, okay, so now we see what a joule is and a calorie. How does that relate to other things? Well, here's an interesting little explanation. Turns out that watts is the normal thing we have around the house. When you plug in your toaster, it's about 1,000 watts. So what's that? That's the amount of power going into the toaster to heat up your bread. And so how does that relate to what we're talking about? Well, it turns out that you can relate watts to joules to calories. And so all those things are now interrelated, courtesy of Mr. Joule's experiment. So in this particular case, I took a 900 watt Mr. Coffee coffee maker and brewed a pot of coffee. And it was 540 watt seconds. That's equivalent to about 540 kilojoules. So now we have watts related to joules. A watt is simply a joule per second. Then it costs about 3 cents to brew that cup of coffee, and the amount of kilojoules compared to food, which is what we're interested in today, is about a fourth of a Big Mac. So in theory, if I ate 3/4 of my Big Mac, I could use the other quarter to heat my coffee. And of course, that's not a practical thing, but that's what the math says. Now here's another interesting use of those temperature units. If you take the 2,000 calories per day, which is the USDA nominal figure, and we'll see some details on that, and if you do the energy conversions, you convert the kilocalories to joules and to watts and so on, it turns out that the 2,000 kcals per day amounts to about 413, about 96.8 watts. So what happens as you're burning your 2,000 calories per day, you're throwing off heat to the extent of about 96 watts. So you're running around like a 100-watt light bulb. So that's the relationship between food calories and conventional energy units. Now, your brain, we'll see in a second, takes about 1/4 of that amount, or 1/5 of your total daily energy to keep you going. And that's about 3/4 of a Big Mac. People use Big Macs as an index of energy. It's common usage, kind of fun. Now, those 2,000 calories I mentioned Here's a chart. This shows the kilocalories for women. And by the way, when we talk about calories in this experiment and all over the world, we're talking about kilocalories. The actual calorie itself is very small. It's only the energy required to heat 1 gram of water, which is small, by 1 degree centigrade, which is also small. So double small means it's almost insignificant. So we use the kilocalories. 1,000 calories is what's normally meant. So whenever you see a sign on the wall saying how many calories, it's kilocalories, not just a little calorie. But in this chart, it shows that ladies, if you looked at the 2,000 kcals per day, about a 120-pound person and moderate activity. Now, if you're a couch potato, you don't need that much energy, and if you're an athlete, you're going to need more. So your fuel depends on your activity level. Now, for the guys, it's a little different. Guys tend to be bigger. The average mass of the lady in these charts was about 120 pounds or 55 kilos for women. And for a guy, it's a bit more, 154 pounds or 70 kilos. And so guys take a bit more. And so unless you're a couch potato, you're going to need something in the order of 2,400 kilocalories, not 2,000. Now, where do all those calories go? Well, mostly it goes to making heat. Here's the breakdown of the energy demands of your body, and looking at the chart, your brain takes about 19% of the energy to keep going. About the same as a laptop, by the way. We'll see. And then your heart and all of your bodily functions. This chart will show up on the video. You can look at it. The point is that this activity within your body results in making heat. So that's what keeps you warm. That's the 96 watts that you're consuming as a rate. Here's the data on the brain. The brain has been studied quite a bit. Here's 5 people who independently came up with the conclusion that the brain requires about 20 watts to function. So that's about 1/5 of your daily allotment. Now let's get to the experiment. So now we understand what calories are and joules and the conversion between different energy units. So our experiment consists of burning food. And here's the little cartoon showing how it works. So we're going to put the food under this little chimney, and the heat will go into this little water bottle. We'll measure the energy transfer into there by measuring the temperature rise. Now we know the temperature rise, we know the mass of the water, so we calculate the calories, which is simply the mass of the water times the temperature change. Now we're using centigrade. We could have used Kelvin, but they have the same size degree, and we're taking a difference, so it doesn't matter. So what we're going to do, first of all, this thing isn't very efficient. This is kind of it's a high school, beginning college lab type piece of equipment. And you can imagine that it's not terribly efficient. Some of the heat's going to go up the chimney and not hit the water bottle. We used to use this old guy. This is kind of ugly, but it's a bit more efficient. The can was metal, so it transfers heat a little better, and this has insulation, so most of the heat goes into the apparatus. That runs around 75% or 70% more or less efficient. I ran a test this morning on the new setup, and it's a little less efficient. It's around 50%, but we'll measure that right now. So here's the alcohol bottle. What we do is we burn some alcohol, because alcohol has a very well-defined heat content. And so what we do is we'll measure the heat rise due to burning a certain amount of alcohol, and then we'll calculate the number of kilocalories per gram, and then compare that to the literature. Now, it turned out when I did it this morning, we had about 50%. So what that says is that half the energy from the alcohol bottle is going into our receiver, and about half is going out into the air. So here's the calculation. Here's how it works. Calories are measured by multiplying the temperature change times the mass of water. So if you had 100 grams of water, and if you had a 5-degree temperature change, it would be 5 times 100. So that's what we're going to do. Then we will measure the amount of alcohol that was consumed by weighing it, and then we can figure out the kilocalories per gram. Now, theoretically, it should be 7. Practically, this morning, it was less. So it came out to be around 50% efficient. The old setup was more like 70. So we'll look at that right now. Now, what do you do with that data? Well, now you know how much heat is actually going into the water that is relative to the food or to the fuel. And there's a percentage. Some of it escaped. So we'll take that percentage. Let's say it's 50%. And if I came up with a food value of, say, 5, then I would actually have 10 because it was I had more. I had half the energy was going up the smokestack. So here's a typical calculation. This is for the older setup, and so you multiply the change in temperature times the mass of the water, and you come up with a number of calories. Calories are simply mass times delta T. Then what I do is I take that value and I come up with a number. This had to be 5 kilojoules per gram, divided by the mass of the fuel that was burned. And in theory, it should have been 7. So this was 70% efficient. So when I burn the food, I use that correction factor to adjust the readings. Now, we had done in the past a setup. We normally run 2 trials. Now, for the video, we're not going to do that. It just takes too long because we have to do the calibration of the equipment, and then we have to burn the food and measure that. So it's a sequential project, and it takes a bit of time. So what I did is I've pre-done some of this material. So let's go ahead and show you how it works. First of all, we need to know the mass of water that we're heating up, because that's the calculation. So we'll put this little bottle on the scale, we'll tare it, and we'll put enough water in to be about 100 grams. It doesn't have to be exact, as long as we know what it is. So there it is, 106 grams. Write that down. (106.00010). Okay, so that's the mass of water. Now what we need to do, since we're looking at the temperature change, we better know what the temperature was to start. So we can go ahead and put this in the chimney. Now a little cute little thing, you rotate it and now it won't fall out. So it goes into this little chimney affair, and we take a measurement of the temperature. Okay, so we've measured the mass of the water. That was 106.1 grams. We measure the starting temperature. That was 23 degrees centigrade. So now what we'll do is we'll take the little, we have to weigh the alcohol container. So we tear the machine and we weigh it. And this says 184.95. So that's the starting alcohol. Now when we've burned some, it's going to be less, and the difference is going to be the grams of alcohol consumed, and we know how many calories per gram it makes. So here's the alcohol in the container. We'll go ahead and light it. So there it's lit. And we'll wait a couple minutes. Now we want to pick up at least 15 degrees. What will happen is the heat from the alcohol flame is heating the water inside that flask, and when it gets to be about 15, 20 degrees, we'll stop, and then we'll take more measurements. We'll see how much the temperature has gone up. The mass of the water hasn't changed, but the mass of the alcohol will, because we've used some. We burned some of it up. So we'll let go for a little bit, and then we can calculate the efficiency of the apparatus. So let's go ahead and maybe stop short. I already did this morning, so we can use this morning's numbers. The point of the exercise is that you want to see how this whole thing works. So let's go ahead and stop this, and you stop it by taking it out, putting a cap on. Now we need to know how much we burn, So we put it back on the scale, and now it's 184.4. So we lost about half a gram. So we did pick up some about 10 degrees difference in temperature. So that's the calibration. And as I mentioned this morning when I did it, it turned out to be around 50%. So about half of the energy is going around the flask and not into it. But we know that now. So we can use that to measure our food product and make a correction. So let's dump this water, and I'll put in some fresh water. So now we're ready to do some food. So the sequence is exactly the same. We want to put roughly 100 grams of water in this flask. So what we'll do is we'll go ahead and put the flask on. We'll tare it so we don't have to do subtraction. And we'll add enough water to make it about 100 grams. Again, the amount isn't important as long as we know how much it is. Okay, 103 grams. So now we put it back in the setup with a thermometer. Now we want to measure the temperature again. Another visual. Oh, this one's a little easier. This one looks like it's 27. So it's 27 degrees. Rotate it. Let me write that down, 27 degrees. So now we're going to transfer the energy from a burning food into the calorimeter. So what we want to use is a Cheeto. Why Cheetos? Well, I've got all these things we could pick. Cheetos are kind of fun because they burn nicely. They have a lot of oil in them. Probably not a good health food, but they burn nicely. So we'll light it. Lose a little energy because we're lighting it outside. Oops, get it going. Okay, now, hopefully you can see in the video, the flame. So that Cheeto is busy burning up. And is transferring its heat energy into the water. Now at some point it's going to go out because it will have consumed all the fuel. But you can see it's burning quite nicely. That's why I picked it. So inside your body, that's burning in a different way, and we'll talk about that in a little bit. Okay, so it's almost burned out. Okay, so now it's done. We've burned up the Cheeto, so you can see it's all black, and we'll weigh it. I didn't give you the weight before, but I did measure it earlier today, and there'll be a chart in the video that gives you before and after weights, and then of course there's a difference in the alcohol, or not the alcohol this time, just difference in weight of the Cheeto before and after. So the difference then in the mass is what burned, and then look at that, all charcoaled up. And then we have the temperature, which is different. It's about 42 degrees. So it did pick up some temperature. It gained temperature and it lost mass. So then we do the calculation to find out what the energy was. So here's the sequence of events that we just went through. First we weigh the flask with and without the water, and then the water is the amount of material that's absorbing the energy. And then we weigh the food before and after, so the difference is the amount that burned up that contributed to the heating. And then we ignite it and put it under the burner like I showed you. Remeasure the water temperature, we did that, and then we come up with some value for the food. So here's some examples. I'll give you the Cheeto data in a minute. Here's the, for a pine nut, for example, we we use pine nuts and walnuts and cashews and all those kinds of things. For a pine nut, we came up with about 4.2 kcals per gram by looking at the calories, which is the mass of water times the change in temperature, divided by the grams of material burned, and 4.2 kcals per gram. But then we have to fix it with the correction factor. Now, the old equipment was around 70%, so instead of 4.2, it really should have been 6. And the manufacturer says, or the internet says it should be 6.7. So what happened? Well, we were pretty close. 6 compared to 6.7, about a 10% error. Not too bad. Here's 2 more examples. This one is a pine nut and a Triscuit. So those Triscuits are over there. Students like to burn those up. And same calculation is involved. It's the water times the delta T, and then you apply the correction factor for the apparatus. In this case, the apparatus is 74.7. A different semester, a little bit different result. But the error was around 9 to 10%, or 6 to 11%. Now for the Triscuit, which is what I did before we came in today, here was the data. Here's the picture of the Triscuit before, and here it is after. And here's the mass difference, and here's the temperature difference. And then when you do the math, here it is. So here's the mass that got burned up was about 0.4 of a gram, and the final temperature of the water picked up 15 degrees. And so the calories were around 1,500, but that's little calories, so it's 1.5 kcal. And when you do the correction factor, you come up with 74%, you come up with about 5.3, and it should have been 5.7. So not too shabby. So this was around 6 or 7%. Now, how do we know what it should be? Well, it turns out that the manufacturer generally will tell you. Here's a bag of Cheetos, and you'll see on the back it says 160 kcals for a 1 ounce serving. Well, 1 ounce is 28 grams, so that's about 5 kcals per gram. So manufacturers then tell you what's going on. So that's pretty much what we wanted to show you today. The one caveat, interesting thing to consider, is that we know that we don't burn food in our stomach the way we burn it in this experiment. So when people measure calories of different items, they're burning them, but they're not digesting them. So what's the difference? Well, here's an interesting example. This is a buffalo, and that's buffalo poop. So why am I showing you that? Well, because the Plains Indians and the pioneers used to burn that stuff. Made a nice fire. They could use it for cooking and heating. What that meant was the buffalo was not digesting all the material that was going through them. Some of the cellulose doesn't get digested. You can eat all the sawdust you want and it wouldn't make you fat because you can't digest it. So in our food, there's some percentage that's not digestible. So the calories that you see on the labels are a little misleading in that they're measured a different way. They're not measured by metabolism. So that's about it for the thing. So let's go burn something.